Hello, everybody. Welcome back to the Insightful Thinkers podcast, number 14, another Monday morning. And hope you guys had a good weekend and hope you guys get a good start to your week as well. Today, we are going to be discussing the structure of scientific revolutions. How do scientific revolutions happen? What are the characteristics of a scientific revolution, and what are the effects of a scientific revolution, and other things like this. And we're going to do some in-depth analysis into some science things again today, which always interest me. So the source for this episode is Thomas Kuhn's 1962 book titled by the same name, The Structure of Scientific Revolutions. This is one of the foremost books in scientific philosophy, and Thomas Kuhn's one of the most influential philosophers that science has ever seen. He was a Harvard philosopher, and he wrote this book kind of detailing what scientific revolutions are all about. So let's talk about that today. And there are going to be some of my own ideas sprinkled in here, but it's mostly going to be ideas from Thomas Kuhn that I want to kind of communicate to you guys and to hopefully simplify a little bit, because it was a little bit of a verbose text, as a lot of psychology texts are, and so very wordy, and but very a lot of information was in there as well, and a lot of effective communication of his points. So I just figured I might as well try to share some of these with you guys today, because some of the things he was talking about were very interesting. So before we dive into what scientific revolutions are, we have to know what is science in the first place. So science is the systemic study of the world through observation and experiment. So when a lot of people think science is a bunch of people peddling their own ideas without much support and without much kind of content there, and they're just trying to peddle their own hypotheses and theories. And there is a little bit of that, but that can't, even though there is some of that, it still needs to have some kind of a foundation to it and some kind of a meat to it when scientists create scientific papers. Scientific papers are meant to inform, not to entertain. There's no creativity really involved in scientific writing, for better or for worse. And for science, it seems to be for better, because scientific writing is not about, it is about creating things, but it's not about trying to use special language. You have to be succinct, you have to be to the point. There's no ambiguous language really in scientific writing. It's not a stream of consciousness. There's no type of poetry. There's no there's nothing like that. It's not abstract thinking. It's concrete thought that is developed through experimentation, and all the references in there are not your own ideas. They're references and ideas from other publications to support your paper. So it's a very objective field, is basically what I'm trying to communicate to you guys. The scientific method, how do we create these scientific papers in the first place? Well, it starts with an observation, and then you have a hypothesis, which is a proposed explanation made on the basis of limited evidence. Then you have an experiment to test your hypothesis and to test your question of, is this the way things are? And then you analyze your data, and then you make a conclusion. And this conclusion either supports or refutes your hypothesis. And if it refutes your hypothesis, you reconstruct your hypothesis, and you indicate in the discussion of your scientific study what changes could be made in future experiments to maybe test your idea in a better way, or to essentially to test the idea in a better way, or to test another idea, or different experiments that could eventually support the hypothesis that you initially tested in this experiment. So I hope that gave you guys a decent overview of what science is. Now, what is a scientific revolution? Here is this thing we have called science, where there are a lot of established principles and theories based on the backs of a lot of brilliant researchers. But how do paradigm shifts happen? How do revolutions happen to change what we know as science? So scientific revolution, what is this? So scientific revolution are developmental episodes in which an older paradigm is replaced by an incompatible new one. So what is a paradigm? Well, a paradigm is the distinct set of concepts that are shared by members of a scientific community and are considered legitimate in the field at the time. So there are certain, as science has progressed, there have been certain paradigms and ideas that many scientists have subscribed to at a certain point in time until this ground gets shaken and the foundation is shifted when a revolution happens, because a new development occurs when an older paradigm gets replaced. So that's essentially what a scientific revolution is. And these scientific communities who have the similar ideas and share ideas about a paradigm, they kind of get fractured, and some parts of the community hold on to the old paradigm and some of them move on with the new one. And at a certain point, every scientist is almost forced to conform with the new one when more evidence comes out to prove that theory. Scientific revolutions, Kuhn states, are very similar to political revolutions. So political revolutions, they're inaugurated by a growing sense that existing institutions no longer solve the problems posed by the environment that they have in part created. And scientific revolutions in a similar way are inaugurated by a growing sense that an existing paradigm has ceased to function adequately in the exploration of the aspect of nature to which that paradigm had previously led the way. So in both political and scientific developments, there's some kind of a sense of malfunction that exists, and this leads to a crisis in the field, which leads then to a revolution. So at a certain point, in science, the certain paradigm of the day cannot solve all of the problems that it once did, or that it even helped to solve, to create in a certain way. And this leads to a crisis where eventually these scientific communities realize this theory that we've been following, it's not entirely accurate, and this creates this crisis state, which eventually leads to a revolution. And Kuhn says it's very similar to politics, where a political revolution happens where there's some kind of an unrest because the institution that's in place clearly is no longer solving the problems that it needs to for there to be peace. So it kind of is like a scientific revolution. You could think of like the French Revolution, which more people maybe know about, where there's some kind of a growing unrest and things almost need to change because that what is in place is no longer sufficient. So what is this crisis that comes from? What is this growing unrest or this crisis that comes from the imperfection of the current paradigm? Well, the crisis that happens is this growing evidence that a theory is not entirely accurate in predicting outcomes. Well, what is a theory in the first place? A theory is a system of ideas that explains a large number of phenomena in the natural world. So an example of a theory would be Copernicus's theory of heliocentrism, the theory that the Earth and planets revolve around the sun, and the sun lies at the center of the solar system. So this is a theory, and this theory, it's a theory because it explains much of why we observe what we do in the universe, and it allows us to make a litany of predictions about how the solar system works. And this is what makes it a good theory. A theory can create testable predictions, and it constantly gets confirmed by a lot of different predictions in a lot of different fields. Excuse me. And but when a theory like this is not working, is no longer working, crisis arises. And the reason Copernicus developed the theory of heliocentrism was because crisis was arising in relation to Ptolemy's theory of geocentrism, that the Earth was at the center of the universe. This created, although geocentrism did create a lot of good predictions, it wasn't fully accurate. And this created a lot of unrest, which led to Copernicus developing the theory of heliocentrism. So the crisis is like a prerequisite to the scientific revolution, where there's this growing evidence that the theory we're using right now is not quite accurate in predicting outcomes. And that causes a lot of unrest in the people, just like political revolutions that happen, like the French Revolution. There's some kind of a growing unrest that leads to a scientific revolution, is what Kuhn was trying to get across in this book. So another prerequisite to scientific revolutions, along with this crisis state, is there's a proliferation of versions of a theory, or the constant tinkering of a theory to achieve desired experimental results. So when this crisis is arising, when scientific communities are realizing that this theory is not fully accurate, they tinker with the theory and they make small changes, and there's a proliferation of different versions of the theory, and it's all spawning from this imperfect ability for the first theory to do its job. So, for instance, astronomers attempted to eliminate each newly discovered discrepancy in the Ptolemaic theory by making constant adjustments in its underlying mathematics. The Ptolemaic theory was the theory of geocentrism, that the Earth was the center of the universe, and it actually did a pretty good job in making a lot of predictions about where stars were going to be, where different things were going to be at different times, but it wasn't quite right. So this caused a lot of tinkering by other scientists in the mathematics, and proliferations of the theory were made, and version 1, version 2, and these are signs that the theory wasn't quite right. And So this is really a prerequisite to the revolution. When you see a lot of proliferations of a certain theory, and they tinker with it to achieve the desired experimental results. I liken it to I don't know if you've ever, maybe in high school, where you were doing a math problem and you just didn't know how to do the question, but you almost found a way to do it, and you tinkered with the way that was taught, and you ended up with an answer that was maybe similar to one of the multiple choice answers. So you end up just choosing that one. Almost you're a couple numbers away from one of the answers you see, and you choose that answer. So it's not quite right, and you feel off about it, and you know what, this isn't quite right, but it serves its purpose to get close. But you're building your answer off of a totally incorrect method, and this is what is happening before these scientific revolutions happen. So as time went on, though, these astronomers who were initially tinkering with the Ptolemaic theory that the Earth was in the center of the universe, they realized that a discrepancy corrected in one place was likely to show up in another. So they were almost taking a step forward and 2 steps back in certain ways. And although they were making changes that, now it works with this experiment, but then with another experiment, it totally threw everything off. By the early 16th century, then, an increasing number of Europe's best astronomers were finally recognizing that this astronomical paradigm was failing in application even to problems that it was built to solve in the first place. And this is the type of recognition that was the prerequisite to Copernicus's development of heliocentrism. So Kuhn really is getting into the weeds of how scientific revolutions arise. So it's really this crisis state due to the theory not solving what it needs to solve or predicting what it needs to predict, and this proliferation of a lot of different theories and tinkering. And these are signs that something new is going to arise that actually is right. And heliocentrism ended up being that thing compared to Ptolemy's geocentrism. What are some characteristics of the works that trigger scientific revolution? So, for instance, what are the characteristics of Copernicus's work? I don't actually know what it was called, but the work where he proposed heliocentrism. What makes these works unique? Or Newton's Principia Mathematica, I believe it was called, where he talked about the theory of gravity and totally made a groundbreaking change and a revolution on his own. So what is it about these works that causes a revolution? Well, these works, the work is sufficiently unprecedented to attract an enduring group of adherents away from the competing modes of scientific activity. So the work is powerful enough that it attracts a lot of people, and it can be a revolution if scientists don't hop on the bandwagon. So that's one thing. It's so unprecedented that people end up subscribing to it rather than the old one. The work is sufficiently open-ended to leave all sorts of problems for the redefined group of practitioners to resolve. So it is a scientific revolution cannot come from a work that is closed-ended, where you might read it and say, oh, that's kind of cool, that's different, but how does it predict new things? How does it apply to different disciplines? If it can't do that, it can't trigger a revolution. The work also resolves some outstanding and generally recognized problem that can be met in no other way. So, for instance, when you go to Copernicus's heliocentrism, there was really no other way to resolve Ptolemy's errors than to totally shift the thinking in science at the time, so that you couldn't just tinker with a theory that had the Earth at the center of the universe. Your predictions might always be kind of close, but they were never going to be exact because you're just looking at the universe in the wrong way. So Copernicus came up with a solution that there was really no other way to fix Ptolemy's system rather than to totally shift it and say, no, the sun is at the center and the planets revolve around that. So that's another characteristic of these revolutionary works. The problem can't be resolved in any other way. The work also defines the legitimate problems and methods of a research field for succeeding generations of practitioners. For instance, Copernicus' heliocentrism, it wasn't just a one generation thing where all scientists at that time said, oh yeah, maybe the Earth does revolve around the sun, and then all of a sudden they went back to Ptolemy's system. This is something that has stuck around till 2020 or whenever you're listening to this, and it's not going to go away. That's what happens. It defines the problems legitimately for succeeding generations as well. The implications of the revolutionary work are often unclear as well, or even opposed sometimes. And Copernicus, again, this episode could equally be titled Copernicus heliocentrism or something, because I'm going to talk about him a lot more in coming areas too. But we'll talk about Copernicus again in this example, where his work was totally opposed by the church, who obviously did not want the Earth not to be in the middle of the universe. And when Copernicus correctly identified that we were all wrong in thinking the Earth was at the center, the results were suppressed, and he faced terrible things against him, similar to other scientists. I believe Galileo experienced similar things from the church when he was making some of his findings, some of his astronomical findings. So the implications of the work, they're often opposed because it's such a revolutionary paradigm shift, and people aren't ready to just adopt that. Similar to Darwin's natural selection, it's going to take a long time before more people are going to be ready to adopt that natural selection is a principle that operates in the world. Some people just write it off due to whatever it may be. So the implications of the work are often opposed and often unclear. So it's often we don't really know exactly where it's going to take us, and oftentimes the paradigm shift is not 100% accepted right away because we've been so used to following the old theory that it takes a long time before the new theory starts to permeate a little more and becomes verified enough by new experiments that scientists now hop on that new bandwagon. So another thing that these revolutionary works do is that they transcend disciplines very well. So, for instance, if there was no X, there could be no Y. They're very influential. Think about Sigmund Freud's ideas about the unconscious mind and how the unconscious mind operated. Before that, nobody really thought about the unconscious mind, and people only thought about how we operated as conscious beings. And although his theory And it's hard to even call it a theory because it didn't really even generate many testable hypotheses, but it was very influential, and it did create a revolution, and it totally spawned new fields in psychology, subdisciplines. He influenced, as I mentioned in the last episode, Carl Jung and all sorts of psychoanalysts. And even to this day, there's psychoanalytic therapy. So it was very influential. And he influenced other disciplines, as I mentioned. So surrealism actually was a movement in modern art that what they tried to do is they tried to paint pictures without thinking. And this was directly related to Freud's ideas about the unconscious mind. And they tried to paint, for instance, Salvador Dali, he painted kind of as if from a dream, and a lot of his paintings, they look very dreamlike. They don't make a lot of sense. And this comes from Freud's ideas about dreams and the unconscious, and he basically spawned surrealism. So if there was no Freud, there would be no surrealism. And that's another characteristic of these influential works and influential people, is that their work transcends disciplines. You look at Newton's gravitational theory as well. He made so many predictions and transcended just about every discipline. You look at physics, engineering, mathematics, architecture, they all use principles from Newton. So these are the characteristics of scientific revolutions. Now, what are some things that revolutions do not necessarily do, or that works that create revolutions do not necessarily have? Well, revolutions do not necessarily come from a theory that is more accurate than the previous one. So there's a good example of the pendulum and the falling versus a falling stone. So before Galileo, a pendulum was looked at as a falling stone due to Aristotelian mathematics and dynamics. Aristotle, he thought of a pendulum as a falling stone, and he created essentially no mathematical principles that described it in its constant pendulum motion. But once it was looked at in a different way by Galileo, more predictions could then be made based on his new mathematics that he created. So the idea is that although the pendulum can just as accurately be described as a falling stone, and Aristotle's predictions in mathematics did still work, the revolution happened only after Galileo looked at it as a pendulum, because the new idea could generate more predictions of similar events. So the idea that the revolution happens not necessarily because this new idea made more accurate predictions or was more accurate, but just because it creates more possible options for science to go into the future. So once Galileo looked at it as a pendulum, then more predictions could be made about similar events. So, for instance, from the properties of the pendulum that Galileo gleaned, he derived arguments for the independence of weight and rate of fall, as well as for the relationship between vertical height and terminal velocity of motions down inclined planes. So once he thought of it in a different way, it was just as accurate as Aristotle looking at it as a falling stone, but by looking at it as a pendulum, now there could be way more ideas by other scientists in the future. And that's what can make people hop onto the new bandwagon. Not necessarily because he was more accurate, but because it created a lot more new predictions. Look at the example of the Ptolemaic theory versus the Copernican theory. As we've mentioned, where Ptolemy, it was that the Earth was in the center of the universe, and Copernicus was that the Earth revolves around the sun. So Copernicus's theory, it actually wasn't much more accurate or any simpler really than Ptolemy's, and it did not lead directly to any improvement in the calendar even. So really, you might wonder, if Copernicus' theory wasn't even that much more accurate, why did that become the new theory? Why didn't we just stick with Ptolemy's? Well, part of the reasons were due to the crisis we talked about and the unrest where Ptolemy wasn't quite right. But Copernicus didn't seem to be much more right initially after he proposed heliocentrism either. Well, you might ask, so why does the paradigm shift even happen if the new theory is often hardly more accurate? Well, what happens is that evidence is eventually drawn from other parts of the field and also from other fields. So the new paradigm shows that it permits the prediction of phenomena that had been unsuspected while the old one was used. So even though Copernicus' theory wasn't even much more accurate, what it basically just did was similar to what Galileo's thinking of the falling stone as a pendulum did. It basically allows prediction of more phenomena that had been originally unsuspected if you used Ptolemy's theory. Ptolemy's theory kind of constrained thinking and it couldn't really predict much new stuff. But once you switched to heliocentrism by Copernicus, now everything started to make a lot more sense, even though it wasn't even much more accurate in predicting motions of the Earth and things like this. So Kuhn says an interesting thing. He says, kind of talking about this idea that the new theory often isn't much more accurate than the initial one. He says if a new candidate for a paradigm had to be judged based only upon relative problem-solving ability, the sciences would experience very few major revolutions. So if it was all about new theories creating more accurate things, we wouldn't really have any new revolutions. It's not about it being more accurate. It's about it generating more predictions and for more areas to now coexist better with this new theory and make a little bit more sense. So in sum, almost the same events and predictions are often made from the new theory, but the new theory simply allows things to be looked at in a totally different way and for more phenomena to be observed. And because the new paradigm is often not necessarily more accurate than the previous one, scientific revolutions do not always happen immediately after a groundbreaking work. So because it may not be much more accurate, this is why there's a little bit of a lag before the new paradigm gets accepted. So in the case of Copernicus, again, it wasn't until almost a century later when Kepler's tables were shown to work more sufficiently with the Copernican system when many astronomers finally converted to Copernicanism. So often it takes a little while for other groundbreaking experiments to happen that support this new paradigm when that paradigm finally starts to become accepted. Also, you look at the wave theory of light. So the wave theory of light actually wasn't even as successful as the corpuscular theory in resolving the polarization effects that were a principal cause of the optical crisis. It wasn't until later, in a similar way, that experiments from other fields proved it to be true, shifting the paradigm in physics. There's often a little bit of lag, and you got to give the theory some time to generate new experiments and for new experimenters to come and test the theory when it finally starts to be accepted by more people. So Darwin has a great quote about this, and he showed a lot of foresight with this quote, talking about his own theory of natural selection. And he says, although I am fully convinced of the truth of the views given in this volume, he talks about, I believe, On the Origin of Species, his landmark work. He says, I by no means expect to convince experienced naturalists whose minds are stocked with a multitude of facts all viewed during a long course of years from a point of view directly opposite to mine. But I look with confidence to the future, to young and rising naturalists who will be able to view both sides of the question with impartiality. So he shows a lot of foresight, showing this idea that he doesn't expect that his ideas are going to be accepted right away, but maybe in 1, 2, 3, 4, 5, 6 generations, people are going to start to finally assume his theory, which has proved to be the correct theory in biology. Not without its flaws, and it took a little bit of manipulation, and I guess that's a little bit scary because we did just talk about how one of the first things that happens when a revolution is on the way is that there's a crisis and there's modulating of a theory. The difference with natural selection, though, is that these modulations only built upon Darwin's original ideas rather than totally tinker with the underlying principles of it. But who knows? You never know. Give it 100, 200, 300 years. Who knows if there's going to be a serious revolution in biology that will actually explain even more. Darwin's natural selection just explains how this difference between survival and reproduction happens, and how exactly life exists, and how competition eventually leads to differences in survival among populations. And we're not going to get into it in this episode too much, but the idea is that his underlying theory has proven correct to this date, but kind of like there are people building on it and tinkering it with it, you got to wonder, could there be a serious revolution that happens that at least shakes this up a little bit? And we'll see. But right now we have no better theory to explain the proliferation of life on this planet. In a similar way, Max Planck, who was equally influential to Darwin, he laid the groundwork for the quantum theory. Among other things, he says, a new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die and a new generation grows up that is familiar with it. It takes time for a revolution to gain a stronghold, even in the minds of some of the most brilliant people in the world, and let alone the minds of the public. The minds of the public may take a little bit longer. But eventually, old schools gradually do disappear. And in part, their disappearance is caused by their members' conversion to the new paradigm, Kuhn says. So some scientists do cling to older views, but they're simply read out of the profession, which thereafter ignores their work. When you do cling to the old ideas, if people did cling to Ptolemy's theory, people are not going to read your work because eventually your theory doesn't have as much evidence supporting it as the new theory, which caused the paradigm shift. And in reality, those unwilling or unable to accommodate their work to the new theory or the new paradigm eventually just proceed in isolation or attach themselves to an outcast group. So the idea is just that if you cling on to the incorrect theory of old, then your group will just be an outcast of kind of this pariah of researchers who kind of maybe believe the same things, but on a broad scale, their work is not actually accepted. One thing that about scientific revolutions, though, as incredible as they are to getting us closer to what we think is absolute truth, what we have to understand is that, we have a bias to the principles of the day and what is true today. But what is true today may not be true tomorrow, and by tomorrow I mean maybe even as soon as 50 years down the road. With the proliferation of technology, you never know how fast these new revolutions are going to occur. But just the idea that we have to understand that scientific revolutions do not always produce absolute truth. And even if it's supported by a lot of experiments, and for all the experiments that support natural selection or the theory of gravity and all these things like this, they eventually can be superimposed or subseded by something new. So I'll quote directly from Kuhn here because he puts it in such an eloquent way. He says, the more we study Aristotelian dynamics, phlogistic chemistry, or caloric thermodynamics, for instance, the more we realize that those views of nature were neither less scientific nor more the product of human idiosyncrasy than our current views of today. If these out-of-date beliefs are to be called myths, then myths can be produced by the same sorts of methods that lead to scientific knowledge. If, on the other hand, they are to be called science, then science has included bodies of belief quite incompatible with the ones we hold today. Out-of-date revolutions, then, are not necessarily unscientific, just because they have been discarded. He's just saying the idea that at one time we did believe in Aristotelian dynamics. At one time we did believe in Ptolemy's theory, and we thought, oh, that's got to be the truth. That's got to be the way things work. But eventually they get superseded and they become almost mythical in a way. But they were conducted in a scientific way. So we have to understand that just because things are conducted in a scientific way doesn't mean they're going to produce absolute truth that is going to persist forever. And we have a bias to what exists now because that's just what we've been taught. And Kuhn talks about what we've been taught in the textbooks and the paradigms we've learned. But eventually these get shaken. And what we think is truth today actually may not be truth tomorrow, which is a little bit scary. But Kuhn really puts that really well, that just because it's conducted in a scientific way doesn't mean it's going to persist forever. We'll close off this episode with some of the effects of a scientific revolution. What happens after a scientific revolution occurs? Well, scientists end up adopting new instruments and look in new places because now more questions have been unlocked. Once Galileo looked at the falling stone as the pendulum, now there are more questions unlocked about constant motion and things like this. So now they adopt new instruments, they look in new places, they see new and different things when looking with familiar instruments, even in places they had never looked before. So they don't even need new instruments to find totally new things in places they were looking before, because now you're just looking at it through a different lens. That's what a scientific revolution causes, and it's really incredible how much it influences science when these revolutions happen, because now all scientists, their work has to totally change to accommodate this new theory. And as we talked about, if you don't accommodate this new theory, you're going to get weeded out. So it's very exciting what these revolutions do. It's almost as if the professional community is suddenly transported to another planet now, as Kuhn says, where familiar objects are seen in a different light. So the same exact thing, when you look at it with your new spectacles, you find so many new things and so many new discoveries. And we talked about in a previous episode where education, we said, is similar to gaining a set of spectacles to look through the world at. And when you become educated in whatever field it is, whether, say you get educated in film, then when you look at movies, you get a more critical approach because the lenses you're wearing are through your education of film and how did he create that shot and what was the underlying message there. Whereas someone who has no education in film may not look at that movie in the same way. They just might think, oh, that was a good movie, that was fun. But you may be seeing totally different things. Similar to a way where if you have an education in science, you look at say it's biology, you look at life in a different way. You look at a lot of different things in a different way, whereas people who don't have that education don't really see the world through that lens. So that's what these revolutions do. They create a new lens for people to look at the world through. The scientist who embraces a new paradigm is like someone wearing inverted lenses, as Thomas Kuhn says. The scientist conforms to the same constellation of objects and nevertheless finds them transformed in many of their details. You're looking at the same exact things, but now these things are totally transformed just due to the paradigm shift that happened. That's the structure of scientific revolutions. I hope I described mostly the book well and how scientific revolutions happen. I hope I described that pretty well and all the characteristics of it. This is coming from Thomas Kuhn. Mostly, a couple of my ideas were sprinkled in there. Notably, the discipline transcendence idea, where the work really transcends disciplines. And Kuhn talked a little bit about that. And but a couple of my kind of things were sprinkled in, but this is mostly, I have to mostly credit Kuhn for writing this book, an incredibly well-written text. It was basically a collection of essays that really summarizes what a scientific revolution is, because I've had ideas about that for a while. How do things where we think that they're truth, how do these truths totally get turned on their head? And Kuhn really did, I think, a good job of talking about that there. Hopefully you guys enjoyed this episode. It is super early morning here, and that's why we actually don't have any sunrise right now. The days are gonna be getting shorter here, and when the winter rolls around, we're not gonna have a lot of light. But yeah, so that's why there's not, if you're watching on YouTube, not the exact same production in the lighting. But either way, you guys, thank you for listening in. Thank you for watching the Insightful Thinkers podcast. This is a great episode. Up until this time, my favorite episode has always been my most recent one, but I still think that Moonlight has been my favorite so far. But man, every episode that I do interests me, or else I wouldn't be doing it. And it's kind of interesting. The catalog of Insightful Thinkers podcast totally represents what I'm interested in. And that is kind of cool to me when I look back at the catalog, and when we're years and years down the road, we can look at that catalog. And I hope what interests me interests you guys as well. And that's why I guess you guys are subscribed. Thank you to all you people who are subscribed on YouTube and subscribed on whether it's Spotify or Apple Podcasts. Thank you guys. If you like this episode, please share it with at least one person who's interested in science, or if you know someone who's also read this book. It's a bit of a kind of an esoteric one that maybe not so many people have just picked up and read. It's not an easy read. As I said, it's got a lot of words, very verbose, but if someone's even interested in science, please share it with them. Please subscribe to the podcast on whatever platform you're listening on, if you're on Apple Podcasts or if you're on Spotify. And if you're on Apple Podcasts, please leave a rating or a review. You can just click the star rating, or you can even write a review. That would be great as well. And if you're on YouTube, please like or dislike the video. Please share your own thoughts with me as well. That's a big thing we're doing at Insightful Thinkers Media. You can do that through the YouTube comments section. You can do it through the Connect page on the website. You can do it through Instagram at Insightful Thinkers Media, or on Twitter at Team ITM. And if you happen to be on the website, feel free to check out the blog posts for poems and other articles. And finally, if you want to join the monthly ITP video conference call, you can support the podcast on Patreon, you guys. But in the end, whatever you guys do, just listening and watching is always plenty. And I'm always grateful for people who are interested in the sharing of ideas and some in-depth analysis, you guys. So if you're interested in that, I'll see you next week for more in-depth analysis into a diverse set of topics. Thank you for listening in, everybody. We'll see you next week. Take care.